In this video we are going to see two very important results. The first result that we will derive is this. Delta of x, which is the Dirac delta function. I'm going to call it function, but actually it is a distribution, but I will not get into these details. This delta of x, the Dirac delta, can be written as an integral from minus infinity to plus infinity of e to the minus I kx dk over 2 pi. And then the second result that we will derive is this. The Fourier transform can be obtained from the Fourier series. Let's start by considering the Dirac delta function. So if I draw this quote-unquote function, so I'm going to call it function as I said, this is x, and the Dirac delta has a value which is infinity at x equal to 0, so I'm going to draw an arrow over the y-axis here to denote that the delta function goes to infinity here and then it is 0 otherwise. But instead of considering just this arrow, I'm going to add the so-called train of impulses. What is a train of impulses? Well, by train I mean that I'm going to consider a series of these Dirac delta functions, just like this. They are periodically repeated over the x-axis, and the distance between each Dirac delta is L. That's the period of the train or of the series of impulses. This is important. Why I'm considering this train of impulses? I'm considering this because in this way, since this function becomes periodic, I can expand it using a Fourier series instead of a Fourier transform. So I'm going to consider the Fourier series, and in this case you have to bear in mind that this is a different function. It is not the Dirac delta function, it is not exactly the Dirac delta function, but it is a series of Dirac delta function. And I will call this series of Dirac delta function delta sub L of x, which can be also written like this. It is a summation with the index n going from minus infinity to plus infinity of Dirac deltas, which are simply translated with respect to each other. So I can write it as delta of x minus nl. But I'm not going to use this expression. Doesn't really matter. What is important though is that I can rewrite this function delta sub L of x as a Fourier series. So I'm going to sum from minus infinity to plus infinity some coefficients c sub n, which are the coefficients of the Fourier series, and then multiply these coefficients by the complex exponentials of the kind e to the minus I k sub n times x, where k sub n is simply equal to 2n pi over L, and this is due to the Fourier series. The coefficients can be calculated using this formula. C sub n is just 1 over L, then integral from minus L over 2 to L over 2, and then here I have the function delta L of x, and here I also have the complex exponential with a plus sign instead of a minus sign, so I have to write it like this and then multiply by the x. Now in the interval minus L over 2 to L over 2, the function delta L of x is just equal to the Dirac delta of x, because I am considering just an interval which is located somewhere here. It contains only one impulse. Therefore, it's as if I have only the Dirac delta. And when I multiply this complex exponential by the Dirac delta, I can evaluate this complex exponential at x equal to 0, and therefore the complex exponential is equal to 1. And when I integrate the Dirac delta from minus L over 2 to L over 2, I will get 1, because the area under the Dirac delta is 1. So the result of this calculation yields 1 over L. Therefore, I can rewrite delta sub L of x equal to sum from minus infinity to plus infinity 1 over L e to the I 2 pi n over L times x And this is the Fourier representation of the train of impulses. And now, how can I obtain the Fourier representation of just one impulse? Or how can I extend this reasoning to just one impulse? Well, we can reason using a limit, because if we let L go to infinity, like this, it means that it's as if the impulses are infinitely spaced apart. Therefore, it's as if I only have one impulse. So this is quite subtle. You have to try to reason in this fashion. Let L go to infinity, and therefore this distance here, here, but also here, they will become infinitely spaced apart. And therefore it's as if I only have one impulse. And I will obtain the representation, which we will see that it will be an integral representation of the Dirac delta. Because if we let L go to infinity, the function delta sub L of x will become delta of x. And the wave number, or you can also call it frequency, the frequency k sub n, which is equal to 2 pi n over L, will be infinitely close to k sub n minus 1, for example, because it will be 2 pi n minus 1 over L. And if I subtract these two expressions, so I take k sub n minus k sub n minus 1, I will get 2 pi over L if you do the algebra here, but this will go to 0. We cannot say the same is true for this, because we also have an integer n, and it can be very large as L, for example. So this expression can also be finite, and also this one. But the difference between k sub n and k sub n minus 1 will go to 0, which means that k sub n will be infinitely close to k sub n minus 1. And therefore, it's as if this difference here will become a differential. We can replace it in the limit as L goes to infinity with dk. And k is a continuous variable. And therefore, we have to replace 1 over L with dk divided by 2 pi. And you see it from here, because 2 pi over L in the limit as L goes to infinity can be replaced by dk. Therefore, this expression here will become like this. Instead of delta sub L, we have delta of x. And instead of the infinite sum, we have an integral, because we are summing quantities that will become continuous. So we have to sum from minus infinity to plus infinity. Instead of 1 over L, we have dk over 2 pi. And then we have the same exponential, the same complex exponential, but we have to replace 2 pi n over L here with the continuous variable, which is k, because in here we have the definition kn equal to 2 pi n over L, but kn will become continuous. Therefore, I can just simply replace it with k and then multiply by x here. So we have obtained this very important expression, which is used extensively, especially when dealing with Fourier transforms, partial differential equations as well. This very important expression allows us to derive the inverse Fourier transform from the Fourier transform. Let me show you why. Let's consider the Fourier transform of a function f of x. So if I have a function f of x, and I multiply it by e to the I kx and integrate over x from minus infinity to plus infinity, I can define this as the Fourier transform of f of x, and I can call it f hat of k. And now, if I integrate both sides of this equation here, let me do it below, I integrate both sides from minus infinity to plus infinity, and here I have f hat of k, and I multiply this by e to the minus I k x dk over 2 pi. In here I have to integrate also the right hand side here, so I have two integrals to carry out, integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, and then I have to be careful here, because you see that I have multiplied the function f hat of k by this complex exponential, which contains a variable x. And here I have an integral that has to be computed over the variable x, but in this case, this x here is a dummy variable. So I might as well change the name of this variable. For example, we can call it x prime. And of course, I also have to relabel f of x as f of x prime. So this would be f of x prime as well. So I have to be careful here and should not confuse the variable of integration x prime with the variable x here, because x prime is just a dummy variable, whereas x here is another variable, it's a different variable, and I will show you in the next few steps. Here I have f of x prime, e to the I, k x prime, and then I have e to the minus I k x, and I also have to integrate over dx prime and dk over 2 pi. Now, the order of integration for this double integral here is not important because I'm integrating over a symmetric region, which is R2, the overall two-dimensional space. So I can integrate first over dk over 2 pi and then integrate over dx prime. That's of no concern. So let's do it here. I'm going to rewrite this expression like this. Integral from minus infinity to plus infinity f of x prime, integral from minus infinity to plus infinity of e to the minus I k x minus x prime dk over 2 pi, like this, times dx prime. Now I can carry out this integral here because we have obtained the result earlier. This integral is just delta of x minus x prime. It's the Dirac delta. And then when I multiply this Dirac delta by f of x prime, the result can also be rewritten like this, f of x times delta of x minus x prime. That's because this delta function has an impulse located at the point x prime equal to x, and therefore I can evaluate this function f of x prime at the point where we have the impulse, because where there is no impulse, the function will just be 0, the Dirac delta function will be 0, and therefore I can simply replace x prime with x inside this function, because where x prime is not equal to x, we get that the result is 0. I hope you understand that. And therefore here we just have f of x, which factors out of the integral, then integral from minus infinity to plus infinity of delta of x minus x prime dx prime. But when we integrate the impulse, we get that it is equal to 1. It's as if the area under the impulse is just 1. And therefore here we have obtained exactly the inverse transform, because this is equal to f of x, and we have shown that f of x is equal to this expression here, which is exactly the inverse Fourier transform that we can define starting from the transform. So it is unique. This is a very important result.